Now let's move on to the next section, which is about electrical safety. But before I go on explaining what electrical safety is, let me first show you. Let me just quickly revise what electricity actually is. So electricity is movement of electrons, and usually electrons move from negative to positive terminal. Right? Electrons move from negative to positive terminal, and in the meanwhile, they have a potential to give off energy, translated to a form of energy, right? And then they return back to the source, and so circuit is completed. Here the switch is on, which means the circuit is complete and electrons can flow. But this is not how current is thought of as. Current is thought of as flowing from positive to negative terminal, and this is only a matter of convention because historically this has been done. So this is thought of what actually this is thought of how current actually flows. Actually, the actual physics of uh, flow of current is quite complicated, and this model here is just a model. And I want you to remember one thing, that all models are wrong. I think E.P. Poxy was a statistician. He said it, that all models are wrong, but some are useful, right? So a model helps us in abstracting and in understanding how a system works. And so in medicine, especially in medicine, as we have no unified theory, and what we call is eclecticism in medicine we have. And so in this scenario, we should rely on models, and our models should be uh, coherent. So when I try to simplify a model, it means that I'm trying to explain it intuitively. And there is a trade-off between explaining the true model, and the true working of a system versus understanding it and then catering it to give us answers and explanations. Uh, in reality, in practice, what we have is that we have conventional current. This current is set to flow from positive to negative terminal, right? So only when a circuit is complete, electricity will flow, otherwise it will not. In mains power supply that we have at home, we have all of us have seen that we have these three pronged plugs. We have this neutral wire which is to the left, and the positive wire here which is called hotline, and the ground, right? So this is not always the case because the faulty wiring very frequently happens. Because the faulty wiring very frequently happens because some electricians, they might not play by the rules and they would switch the hotline here, right? So this can happen. Now in the houses we have a voltage source, then we have a circuit breaker, and then we have a hot wire which is usually denoted by black in UK, and then we have it flowing to our devices that we have, and then inside the device we have certain components, and then we have a neutral wire, and then it goes back to the circuit and then back to the source here. And this neutral wire is connected to the earth, which is our which is considered as our zero or neutral, right? And earth is also considered as the source of a sea of electrons, where electrons can go and flow back in. And this is the casing of the appliance that we have. Now this frequently happens that the casing, the hot wire, it touches the casing of the appliance, and so the current is live in the casing. And in that case, if you are standing here and you are touching the casing, and so you are grounded, right? So electrons can go and flow in the ground through you, and the circuit is complete, and then you can get an electric shock here, right? So in order to prevent that, we have in the switches we have this earth line. What happens is that it is connected to the casing, and if a fault develops, if by accident this happens, current would choose to flow through this line instead of flowing through you, because current always follows flows through line through a line of least resistance. And what is most resistant here? It is your skin. Skin is very resistant, and so this is how grounding actually works. So another word about how power is transmitted, electrical power is transmitted. We have our power plant, where is the where is a modest voltage is produced, and then we have a step-up transformer. Step-up transformer is basically it works through induction, and I will not go into details. So we have these electrical coils and uh, winding of the coils at one side, and the other side we have the other variable windings. This the winding of this side may be lower or higher than this sides, and there is a magnetic induction, and through that we have we can increase voltage by increasing windings at this side. Voltage can be increased. So this is how this is the uh, uh, iron or some conductive core here, right? And so what happens is that increased volume can be outputted from here. This is what the function of a step up transformer is that. And you can see here we have 400 kilovolts of voltage being transmitted through pylons. And the reason why we do that, we have a step up transformer, is that uh, transfer of high voltages through these transmitting lines, high tension lines, is very efficient way of transferring line to the to homes and industries. And then again, because this was a very high voltage current that we were getting, we have a step down transformer. Now winding of that transformer would be lesser than this side, right? And so voltage would drop here, and now we have this dropped voltage from 400 kilovolts to 13 kilovolts from the step down transformer, and from those to our main line, which is 240 volts or 110 volts. In United States, in Northern America, we have 110 volts. In I don't know if it is the same in Canada as well, but in US we have 110 volts, and then this is transferred to houses or hospitals uh, or an industry. And now this finishes our introduction, electricity 101. Now let's move on to what the chapter actually says about electrical safety. Now the risk of electrocution. So we have already covered that body contact with two conductive materials at different voltage potentials may complete a circuit and result in an electrical shock, right? We've already discussed that. Usually one point of exposure is live, which is 120 volts or 240 volts depending upon where you are living in the world, with the circuit completed through a ground contact, right? The physiological effect of electrical current depends on the location, right? Where it is on the body, the duration of it, frequency, magnitude, right, of the shock. Now location is where it is on the body. Let's say for example, if this is the human and heart is here, so if it is close to heart, it would be lethal, right? So location, and if you get, this is your hand and you get you get a shock from here, and so current would want to flow from the area of least resistance, so it will go back from here. And if you are grounded from this hand, right, so it would not just go there to the heart and come back and complete the full circuit here, right? It depends upon the location, and then the duration of it. If you are being in contact with current for a long duration of time, of course more electrons would flow inside it, and then it would lead to more severe effects. And the frequency also. Now let's talk about what frequency actually is of the current. What we have given, what we have talked about so far, what we have discussed is the direct current. Direct current is just plain flow of electrons, right? But what happens is that in practice in homes we have an AC current, which is alternating current. So we have this base value 0 here, and the direction of current, the direction of electron flow, it keeps on alternating from this side to this side, right? And so we have this sinusoidal pattern of electron which is centered at 0. This is uniform, by the way. This looks this is more damped here, but this is uniform transmission of amplitude. And these frequencies, the frequencies of these crests and troughs here is written as hertz. So this depends upon the frequency as well. What we have in AC is that we have low versus high frequency ACs, right? So in the mains we usually have around something 40 to 60 hertz. You can call it 50 hertz. In most places it's plainly written as 50 hertz. So when you have that 50 hertz, that is more dangerous, right? Low is more dangerous. And why is that? Why is low more dangerous? No one actually knows the exact principle why is that, but some say that the electrical transmission of heart is close to 60 hertz, right? And so this is why this can actually disrupt the functioning of the heart, and this could lead to fibrillation. This is why we have, when we use AC in the human body, as we will see in surgical diathermy very shortly, we will see that diathermy, we have very high frequency AC flow, and this causes burns, right, or cut, right, by transferring heat to that area, right? So it depends upon the frequency. So we have if it is DC, where do we use DC? We use DC to defibrillate, right? So defibrillators, they have this high DC voltage here, and they just stops the heart for a second, for a moment, and then this resets the heart and the whole theory that you have here. And then again the magnitude, of course, it is the current, it is the flow of electron that actually is lethal, not the voltage. Actually, it is the flow, it is the current that kills. I have to write it here. I have to write it somewhere here. I think it is the current that kills. It is the current that kills, right? And what actually is current? We did not actually discuss it. Current is measured in amperes, right? Amperes is, it is just flow of electrons. And what is 1 ampere equal to? 1 amp is equal to around flow of 1 coulomb per second, I guess. Yes. And what is 1 coulomb? 1 coulomb is about 6.24 into 10 raised to power 18. I think it is 18, yeah. It may be 15, but you can check it. I think it's pretty much 18. So this is the 1 coulomb has charge, has this charge of these many electrons, right? These many electrons, and so this makes 1 ampere. So it is an amperage that is lethal, right? So we have explained this. Now there is another thing. A leakage current is present in all electrical equipment as a result of capacitive coupling. Now talking about capacitive coupling, let's discuss what a capacitor actually is. I think I would write it here. Capacitor. So capacitor is nothing, just two arms of circuit. Let's say for example this is negative and this is positive. Or if we are talking about conventional current, we have this positive arm and we are assuming that current is flowing from here, and this there is dielectric uh, or a non-conductive material which is sandwiched between these two arms. So what happens is that when we get a flow of current from here through a source, this the charge gets built up here and it cannot flow from here to here, right? Talking about DC current here, what will happen that it will keep on accumulating at this end until and unless there is a circuit here, and then it will flow from there. In AC, when in AC there is some charge can flow out and leak through these two surfaces, and this is what is happening here. We have this person touching this casing and there is an EMF here through capacitive coupling. So some charge is leaking through here and then he's grounding and then it is going to the circuit and he's getting the electrical shock. So there is one way of preventing that, is that there can be doubly insulated casings. So if for example a hot wire touches it and then it becomes live, and if we have a double insulation, then we will not be completing this circuit here. Other monitors are designed to be connected to a low impedance ground. See the safety ground wire, which we have already discussed, how the ground works. That should divert the current away from the person touching the instrument's case, because current always flow through the path of least resistance. Now, the magnitude of such leaks is normally imperceptible to touch. It is really low. These leaks, as low as 1 milliamperes, and well below the fibrillation threshold, which is about 100 milliamperes. But as we will see shortly, if the current bypasses the high resistance offered by skin, however, if there is a breach of a skin and if there are certain lines there, we have some invasive lines, and current is directly applied to the heart, current as low as 100 microamperes, or which is called microshock, may be fatal, and so this could cause fibrillation. This is the reason why the maximum leakage allowed in operating room equipment is about 10 microamperes, because 100 microamperes of uninterrupted current uh, can lead to fibrillation. So cardiac pacing wires and invasive monitoring catheters, as I've explained above, provide a direct conductive pathway to myocardium and blood, and normal saline can also serve as electrical conductors, right? So what is a conductor? Conductor is something that can give off electrons. And what we have in our saline, let's say for example, or fluids, we have ions inside it, and ions pretty much function as electrons or charged particles, so they can also cause flow of electricity. So the exact amount of current required to produce fibrillation, as we saw that it was 100 milliamperes, uh, which is the cutoff for fibrillation, uh, ventricular fibrillation. So the exact amount of current required to produce fibrillation depends on timing of the shock as well, related to vulnerable period of the heart repolarization. So heart repolarization corresponds to the start of T wave on the ECG, right, or EKG. Now the other section is protection from electrical shock. What can we do to be protected from electrical shock? What measures can we take? So although direct patient grounds should be avoided, of course we should, in every way we should try to avoid grounding patients so that circuit is not complete and current doesn't flow. But this is almost impossible because we have an operating room environment. There are metallic objects there, and then there are wet. This is a wet environment. We have salines there. Blood is a good conductor of electricity, right? So this is not feasible. It is not possible to do that. So instead, there are certain things we can do. So one of the things is operating room power supply can be isolated from ground by a device which is called an isolation transformer. I will not go in more details about isolation transformer here because this would be very detailed and it would require lot of time to actually understand how a transformer actually works and how the windings and happens, and then how the voltage, current, and resistance is linked through equations in a transformer. So I would just point out that these two circuits here is the windings that we discussed here, like an ordinary transformer, and then the secondary windings here. So this is the high output, high voltage system here, and then this is the secondary output system that we have here. So these systems are not connecting, right? This is a ferromagnetic core that we have where electromagnetic induction, it induces a voltage, and so these are two different circuits here. So even if he's touching and he's ground, he's actually being isolated from this main circuit, so electricity wouldn't flow. And so isolation monitor is hence a device which we can implant in our electrical devices in operation theaters, and so it would prevent from giving electrical current. So the line isolation monitor, there is a isolation monitor as well, and together these isolation transformer plus line isolation monitor, they work in tandem, and they work as an isolation system, right? So isolation monitor determines the degree of isolation between these two power wires and the ground and predicts the amount of current that could flow if a second short circuit were to develop, right? And so we have this line monitor, and we can see that it is recording the amperage of current that can flow uh, uh, through a circuit through a defect that has developed, right? But even isolated power circuits do not provide complete protection from small currents capable of causing microshocks or fibrillation. And how does this happen? This can happen through currents or capacitive couplings that we have already discussed. The line isolation monitor can detect all faults such as broken safety ground wires. It cannot detect all faults such as broken safety ground wires within a piece of equipment. It cannot do that, right? And there are, however, modern equipment designs that decrease the possibility of. There are other modern equipment designs that decrease the possibility of microelectrocution, and these include, first of all, double insulation of the chassis and the casing, as we have already discussed, and ungrounded battery power supply is that we have a device, let's say for example, and we have an electrical circuit somewhere here, it is functioning, and then we have this battery power supply here which is ungrounded, and it is applying, this is being supplied the uh, to the equipment that we have, right? And another thing is that patient isolation from equipment connected ground by using of optical coupling or transformers. The line transformers we have already discussed. A very similar concept to line transformer, uh, a concept as in a concept but not in principle, is optical coupling. What happens is that, let's say for example, we have circuit one here, which is a high power circuit, or and then we have another circuit, and what happen is that we have a light emitting diode which emits light, and then we have a transistor here. What has a transistor can variably increase the uh, you can see the uh, conduction of electricity. Now here what is happening is that light is falling off, as it is an optical device. Light is falling off on the transistor, and then this transistor is allowing flow of current here. And so this happens that this way these two uh, potential systems of high versus low voltage can be separated. And with these are this optical coupling system that if you have ever opened a device, you would have likely seen a transistor or a device like that. In the latest edition of the US NPFA 99, risk levels are characterized in the levels as follows. Now there are actually categories that we have in which uh, the areas of the facilities are actually categorized. So what are category 1? Category 1 facility systems are those in which failure of equipments or systems is likely to cause major injury or death of patients or caregivers, right? And category 2 would be facility systems in which failure of such equipment is likely to cause minor injury to patients or caregivers. Category 3 is where such equipment is not likely to cause injury to patients or caregivers but can cause patient discomfort. And category 4 is a facility system in which failure of such equipment would not have any impact on patient care. Right? Category 1 locations and systems will have the greatest amount of reliability and redundancy because they are the one who are following the most stringent of requirements here. And then as the danger goes down, the requirements also go down with it. uh, Under the electrical code of NPFA, operating rooms are defined as wet location requiring electrical systems that reduce the risk of electrical shock hazards. Now, if an operating room is used for procedures without liquid exposure, such as rooms used for central line placement or eye procedures, which is considered as non-wet, as we know that blood is a very good conductor of electricity, facilities can perform a risk assessment and reclassify the operating room as a non-wet area. Now talking about surgical diathermy. What is surgical diathermy? I think most of us have seen a surgical diathermy. And electrosurgical units ESUs generate an ultra high frequency electrical current that passes from a small active electrode, the cautery tip, through the patient and exits by way of large plate electrode, the dispersal pad or the returning electrode. So what happens that this is a diathermy unit and electrosurgical units, and they are generating ultra high frequency of electrical current, which as we have discussed is an AC current. It is high frequency, right? This is very important that we understand that, because if by some fault it turns into a low frequency, which it very rarely does, there are certain case reports, two of them I have read, which if they can turn into low frequency systems, they have a potential to cause what? Fibrillation, ventricular fibrillation, right? And so this is very high frequency, and here is the tip, and then current passes, high intensity current, high frequency current passes through this plate, the patient plate that we all apply to to the patient, and then from there it goes, the circuit is complete. This is a monopolar diathermy. What it means, the monopolar diathermy? Monopolar, it means that the tip has a singular pole and the other pole lies here. Now what is the reason why the burning or the cutting is happening here and not here at this place? Well, the reason is this current density, right? The tip has high current density, right? And the plate has low current density. And so if by fault some way, if the plate comes off and we have a small area sticking to the patient instead of this large area, this can also lead to a burning here, right? So the high current density, as we have discussed, that the cautery tip is capable of tissue coagulation or cutting depending on the electrical waveform. Ventricular fibrillation is prevented by the use of ultra high frequency 0.1 to 3 megahertz compared to that of the power line power, which is 50-60 hertz, as we've already discussed here. The precautions that we can take to prevent diathermy burns, what we can do, we have proper return electrode placement, and by proper, as I've already discussed, it should cover this whole area, and avoid prosthesis and bony protuberance, because why? Because bone is a very bad conductor of electricity, right? So this is why bony protuberances should be avoided, and ideally it should be placed on an area which doesn't have bone or prosthesis. And elimination of patient to ground contacts, and if the patient is grounded, it is being grounded, and of course, and if there is a path of least resistance, then current would want to travel through this, through the from the patient to the ground, right? Current flow through the heart may lead to the malfunction of an implanted cardiac pacemaker or a cardioverter defibrillator. So if we have a defibrillator around here, and surgical diathermy is being done here, and if current flows through that, it can result in malfunction of an implanted cardiac pacemaker. This risk can be minimized by placing the return electrode as close to the surgical field and as far from the implanted cardiac device as practically possible. Now, newer ESUs are isolated from grounds using the same principle as the isolated power supply that we have already discussed, isolated output versus ground reference units. Because this second layer of protection provides ESUs with their own isolated power supply, the operating room's line isolation monitor may not detect an electrical fault. Now this is important right here. Okay. So this is also one of the loopholes of line monitors that can cause hazards. Now, although some ESUs are capable of detecting poor contact between the return electrode and the patient by monitoring impedance, many older units trigger the alarm only if the return electrode is unplugged from the machine. Now we have, let's say for example, this is an ESU and we have this tip and we have this patient lying down here, and it is touching it, and the plate is also touching the patient, and we have that going back. Now if there is a poor contact of the plate somewhere, and there is this would the modern machine would by some way through a meter, it would detect that there is uh, an impedance which is higher impedance here, and then it would actually figure out that the contact is poor and would give off an alarm, right? But in the older units, what was they triggered the alarm only if the return electrode is unplugged from the machine, when the circuit is not being completed. So in older machine, the alarm was given when the circuit, whatever it is, circuit is not complete, right? Now there's another thing we can use, which is just bipolar electrodes confine current propagation to a few millimeters, eliminating the need of for a return electrode. Now another way what we can do is that we have this ESU and we have this uh, electrode that we have, and the returning wire, instead of the plate that we have the returning wire here, we have the returning wire which is wound into the probe that we have, and it goes back to the ESU, to the device, to the source, and then this completes the circuit here, and this is called bipolar diathermy, right? So automatic implanted cardioverter defibrillator device may need to be suspended if monopolar ESU is used. Again, we know why it is, because of a potential of electrical current passing through it and then disrupting its function. And any implanted cardiac device should be interrogated after use of a monopolar ESU to verify that its settings have not been altered by electrical interference.